G'day and welcome back to RC Model Reviews. Today we're talking about wings, flying wings, radio-controlled flying wings. It's a really hot topic because they've become incredibly popular. We had the mini quad craze and now every man and his dog wants to fly racing wings, FPV. So I thought I would do a video explaining how flying wings work and the various factors that affect the way they fly, because although they look very simple, they're actually incredibly complicated bits of physics. And what I thought I'd start with is the basics of how an airfoil or how a wing or how any aircraft actually flies. And of course, it is a balance of four forces. There's always a balance. Nature loves a balance. And so we have four forces, and those forces are obviously, and you would recognize the first one, which is lift. So any wing or any aircraft that's going to fly has to create lift. And that lift is there to oppose the force of gravity, or sometimes it's referred to as weight. Weight is an interaction between gravity and mass, so we'll just call it gravity. So gravity's pulling it down and lift is trying to keep it up. So you reach a point where the two balance and you'll actually get a slight descent. In the case of a glider, it'll come down slowly. In the case of a powered aircraft, then the lift will match the force of gravity and you'll fly straight and level if you want to. Simple as that. Now, obviously, we also have a force that's trying to stop our aircraft from traveling through the air, and that is the force of drag here. And it's not a case of, oh, what a terrible piece of writing, how did I do that? It's not a case of men dressing up in women's clothes at all, contrary to what you may have been told on some of the seedier forums. It's, let me write it properly, I don't know what's wrong with my hands today. Drag is the force that tries to slow our aircraft down, stop it. And of course, opposing the force of the drag is thrust. And that's normally provided by a motor. It can be a jet engine, can be a propeller, motor with a propeller on it, whatever. Or it can be gravity, because in the case of a glider, the gravity is actually providing the thrust as well, because we're traveling down an inclined plane, the glide slope, and it's the fact we're traveling down provides the thrust. I could do the vector analysis, but take my word for it. That's how it works with gliders. Now, okay, those are the four forces. So our wing, most important of all, the thing we really have to focus on here is that we have lift. Lift has to come from somewhere, and that's why we have wings, and that's why they're generally airfoil shaped like this. Now, there's a lot of discussion, there's a lot of argument over how wings create lift. It used to be simple. When I went to school, it was because the air travelled further over the top of the wing than on the bottom, and therefore, because it was travelling faster, the pressure was lower. Mr. Bernoulli discovered this. The faster travelling air produces a lower pressure, so with a low pressure on the top and a high pressure below, you get lift. The air underneath pushes up, trying to push the wing into the low pressure area. That's how lift was created. But there's been discussion since then, and it's waged on and on. No, that's not how it works. Yes, it is. No, it's not. If that's how it works, then how can you fly a plane with a flat airfoil or a symmetrical airfoil that has the same air path around both sides? And the reality is that lift is created by a combination of Bernoulli's theorem, that is the longer path of the air over the top, plus the Newtonian theorem, which says basically you've got air coming along and it's getting knocked down because the wing's at an angle, the angle of attack. This forces some of the air to be pushed down, and it's a Newtonian reaction. For every action there's an equal and opposite reaction. So for every unit of air that goes down, there's a unit of force pushing the wing up. So reality is that most aircraft rely on both principles to work, and talk more about that later. But if we look at lift, lift isn't all that simple. And we've got weight. So let's just look at a couple of things that are related to lift and weight. With weight, we have something called a CG, centre of gravity, normally drawn by this little symbol here. I forget which way, it looks something like that. So it's a circle with broken into four sectors, and two of them are black, two of them are white. Centre of gravity, that means that if you were to put your finger under the wing or the aircraft at a certain point and it balances, that's the centre of gravity. And the centre of gravity is usually quite fixed. It doesn't move around much, unless you're walking up and down the length of the aeroplane. The centre of gravity is fixed, and that's important because we have another thing here, the lift. If you imagine that you had this wing generating lift and you put your finger on the top, then at some point you would balance so there'd be as much lift behind your finger as in front, and the aircraft would balance. The lift would hold it up nice and level against your finger. And that is called the CP, the centre of pressure. It's the opposite of the centre of gravity. Centre of gravity is the focus of the force where the downward force of gravity is balanced, and centre of pressure is where the upward force of lift is balanced. Easy, isn't it? My goodness, but it's not. Unfortunately, it's not. Because when we have a wing like this, it doesn't matter what angle we tilt the wing on, the centre of gravity will remain in the same place. But, and this is really important, the centre of pressure will not. because if you change the angle of the wing's incidence or angle of attack, the centre of pressure will move backwards or forwards depending on the shape of the aerofoil. That is a problem, and that explains why on most aircraft we have tails. Let's look at this a bit more closely. Here we have a cross-section of a wing. It's a lifting section, maybe a Clark wire or anything else, but basically this is a wing that's curved on the top and pretty much flat on the bottom. And I've drawn the two key things here. Here's our centre of gravity, and it's at that point there. And here's this purple area here, this is our low pressure area. So somewhere when we've got as much of that on that side as that side, we'll have the centre of pressure. So let's just say that for the purposes of things, the centre of pressure is here. Okay, so they're basically pretty much in line, and you would think if that's the case, then when this was flying, this would be stable because the centre of gravity and the centre of pressure are aligned, so it's not going to tip down, it's not going to tip up. Simple, you know, the two centre points are lined up so that the aircraft will fly nice and steady and level. But what happens here is most aerofoils, most of the regular aerofoils we have on aircraft with tails, have a very wandering centre of pressure. So if this actually angles up a bit, let me see if I can draw this in a way that preserves the integrity of our drawing. If, for example, we add a bit more angle to our wing, so it goes like this, you can see that. Now suddenly, compared to the incident airflow, we have more angle. What actually happens here is that on most aerofoils, the centre of pressure will be changed and it will actually move to the front of the wing. So that bubble will actually move forward, and that means the centre of pressure, the lifting force, has now moved in front of the centre of gravity. Our CP will actually be up here somewhere. So if you look there, we've got our centre of gravity here, our centre of pressure there. So the centre of pressure means that it will try and rotate the wing around the centre of gravity. So as soon as the aircraft pitches up slightly, it will try and flip right over. Conversely, if the aerofoil nose down, then the centre of pressure would move towards the back of the wing, and so it would tuck under. It would nose up or tuck under. So it's inherently unstable, it has negative stability. Any deviation from the perfect angle will be accentuated by that negative stability. And so that will not work as a flying wing. And that explains why we have tails. Let me just get rid of some of the stuff we're not using, such as that new centre of pressure I put in there and the new airfoil. Let's go back to the old one so we can see what I'm talking about. Here we have the balance again of the centre of pressure and the centre of gravity. They're lined up again. If we now add a tail to this aircraft, like so, and here's our tail, and up here we have our propeller. So here we've got an aircraft. Now what happens here? Very, very interesting. Let's just add a bit of, just put this at an angle because I'm going to talk about something called decollage. I'm supposed to be talking about flying wings, but I'm talking about regular aircraft and stability. This may end up being more than one video. A normal, inherently stable aircraft, an aircraft that's stable in pitch, will actually have more angle on the wing than on the tail. So there'll be a positive difference between the tailplane angle and the wing angle. The wing will always be canted up more than the tail, and that's to give you that stability. This is something we call décollage. It's a French word, which I don't know what it means, but it's a French word apparently, and it just means the angle, the difference between there and there. Because something interesting is going to happen now. Let's say we're flying along at a steady rate, and the aircraft noses up a little bit. But first of all, let's have a look at some of the forces maybe before I do that, because I'm getting ahead of myself here. Okay, so we have lift pushing up here, right? Lift. But down here, this is acting at a negative angle, so we actually have a small force pushing down there. So hang on, have I got this right? Yes, small force pushing down there. So this force here means our centre of gravity is actually going to be in front of our centre of pressure to make this all work. So we don't have that balanced effect before. We have to have the centre of gravity ahead of the centre of pressure. So our CG will be up here somewhere, right? So now our centre of gravity is in front of the centre of pressure. You might think that the plane will want to tip forward, and it will to a degree, but that tendency for the weight to pull the wing down is going to be counterbalanced by this force from the tail, which is actually pushing the tail down, holding the nose up. So there's a balance. Again, I said nature loves a balance. Well, this is all about balance. So the forward CG is balanced by the downward force of the tail. Simple as. Now, when we have an equilibrium, when everything's balanced, the aircraft will be flying along. Let's assume for a moment that the nose of the aircraft pitches up a little bit. Ooh, let's see what happens. Okay, so the nose pitches up. The centre of pressure will move forward somewhat, which will exaggerate the pitch up, as you'd expect. It'll tend to make the nose want to pitch up further. But we're travelling through the air, and there's this downward force on the tail. If the nose of the aircraft pitches up, what will happen? Well, it'll slow down, because now it's having to it's trying to climb, and more energy is going into climbing, so airspeed will drop. You know this if you're flying a glider. You pull back on the stick, it will go up, slow down, and stall, right? And this is what's going to happen here. If the turbulence causes the nose to kick up, then the aircraft will slow. And when it slows, what happens is very interesting. The force from our tail here is reduced because it's not travelling through the air as quickly. Force from the wing will remain relatively unchanged because it's a much bigger area, and usually it's a slightly different section. So if the downward force of the tail is reduced because the air flowing over it is reduced, then there'll be less force holding the tail down, so that the tail will tend to come back up again because this force is reduced. So it will counter the nose up attitude by reducing the downward force on the tail, and it will level out. It's stable in pitch. If we look at it the other way and we say, let's assume that the aircraft noses down, the exact reverse will happen. The aircraft noses down, the centre of pressure will move back, but this is really not important in this case because we have a tail. Once the aircraft noses down, it will pick up speed. And because the air over the tail is now travelling faster, the downward force on the tail trying to push the nose up by pivoting around the CG, this downward force will increase, so the aircraft will go faster and the tail will push down and it will level out again. That's what gives pitch stability. That's the difference between the two angles of the wing and the tail plane. That gives us our pitch stability. Simple as. And that's why also we have a forward CG. Now, you may realise, remember, if you move your CG back, your plane becomes unstable. We all know that. You will try to fly a plane with a rearward CG. It's hard to control. In fact, it may be unflyable because if you move your CG back too far, say to here, then you'll end up trimming. The trimming will be such that this angle here will disappear. You'll end up with the tail like this. So now it's not providing any downward force. So you might as well not have a damn tail on the thing because there's no downward force to oppose the thing because we're balancing around here, doesn't need any downward force. So now you've just got a wing acting like a wing, and when you put the nose up, centre of pressure will move forward. It will make it try and pitch up even more violently. If the nose goes down, the centre of pressure moves back, and it will pitch down even more violently because there's no force being generated by a tailplane in that state of trim. That's why rearward CGs are really hard to fly because effectively your tail disappears. So you might think this is all well and good, but what about the flying wings? How do they fly? They don't have a tail to generate this force. How do they get that stability? How can you get the CG far enough forward on a flying wing that you're going to have, because the critical thing with all stable aircraft is the centre of gravity must be ahead of the centre of pressure. If it's not, it's negatively stable. And a perfect example of this are darts and arrows. You know, we all have, and rockets. Let's say you go to the pub and play darts. There's your dart, like so. It has a heavy metal front here and a sharp point. And they have feathers on the back, and on an arrow it has quills on the back. Why is that? Well, because this is your lifting surface here. So your centre of pressure is going to be way back here where the lift is, right? So you're going to have a centre of pressure way back here with my purple pen for centre of pressure. CP is way back here, and the centre of gravity is way up here. So the centre of gravity is well in front of the centre of pressure. That means they fly stably. They fly stably because the centre of pressure will not move enough to influence the trajectory of the dart. You throw that dart backwards, try and throw it with the feathers first, and it'll flip around because the centre of pressure is, in that case, if you're travelling this way, way in front of the CG, so you have that negative stability. So if it starts to pitch down slightly, it'll flip right round until it's going the right way. So again, centre of gravity must be in front of the centre of pressure, or you'll have negative stability and your plane will try and fall out of the sky, try and flip around and fly backwards. So how are we going to get a flying wing where we can have the centre of gravity in front of the centre of pressure? One moment, please. Right, here's a wing again, lifting wing, relatively flat bottom, curved top. Why can't we just do this? Let's put enough weight in the nose so our centre of gravity is here, because we know our centre of pressure will probably be about here. Doesn't this meet the requirements? Can't we just say, well, this will be stable because the CG is ahead of the centre of pressure? It'll be stable, you know. What's wrong with that? Well, the problem with that, it'll fly like a dart. It'll go, plonk straight down. It'll just dive because this will pivot. You know, basically you've got the centre of pressure behind the CG, it will pivot the wing up and you'll go vertical and you fly straight down into the ground. So it's not going to work. It's not going to work. We need some way to oppose the centre of gravity. Now, on our regular aircraft, we had a tail which was pushing down, pivoting around the centre of gravity to make sure that the plane didn't do a nosedive. We don't have a tail. How can we make this fly like a plane with a tail? And this is where something very important comes in, and we'll call it, because it is, reflex. flying wings have reflex. What's reflex? Well, it's actually just this. The elevons, or the shape of the aerofoil, is such that instead of just remaining flat, it kicks up at the back. Kicks up the back. That does some amazing things to the whole stability and makes flying wings possible. This is why flying wings fly, because of reflex. Because what happens here is now, if you look at it, the air's flying over our wing. We have air hitting here and producing a downward force. So there's a downward force here, which enables us to pivot around our centre of gravity. The centre of pressure is trying to lift up there, but this downward force is opposing it and pushing down there. Because this is a long distance, you can have a lot of lift. You only need a little bit of downward force to balance that lift and keep the plane flying level. Ta-da! This is our tail. The reflex acts as a tail. And again, if the nose does pitch down, then the wing will pick up speed, which means more air flowing over. And because this is further from the CG than that, this will have a greater effect. So the faster you go, the more the downward force trying to rotate around the CG to bring the wing back level. Likewise, if you get disturbed and it starts going upwards, then the airflow over this bit will drop off, and therefore there'll be less downward force. So the weight will tend to pull it round, or this lift will pull the back up, and you'll level out again. It's simple. There's our tail. That's all it is. That's how flying wings work. They have a reflexed wing section. Well, most of them have, well, they all have a reflex to a degree, but there's another way to reduce the amount of reflex, because reflex, it's kind of like, what? We just decided before that lift was created, some of the lift was created by the airflow coming in at an angle and being bounced down, the Newtonian effect. The air that was reflected downwards by the angle of the wing was creating lift, but now we're reflecting air upwards, because if you look at the air flying over this airfoil, it's going to go doot, 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 doot. So instead of being reflected down by the curve of the wing and by the angle, some of it's going to go up. So yes, we pay a price for a reflex. That is, this airfoil is not as efficient as a pure lifting wing, a pure lifting aerofoil, standard flat bottom aerofoil. And that's one of the reasons why flying wings haven't been that popular. You'd think, my goodness, flying wings, no drag from the tail, no weight of the tail. Why aren't all planes flying wings? I mean, why have a tail if you don't need it, if you can do this? Well, the answer is that you're losing efficiency because you're defeating some of the Newtonian lift that a regular aerofoil can create. So for a given area and a given speed, this reflexed aerofoil will not produce as much lift as a comparable flat-bottomed lifting aerofoil. So it's balance. You're gaining stability, you're losing efficiency. So flying wings, but again, it's not that simple. Nothing's ever simple in aerodynamics, because a well-designed, very efficient flying wing will outperform a poorly designed conventional aircraft with a tail. Conversely though, a well-designed conventional aircraft with a tail will outperform a flying wing. And that's why you think, gosh, what about high-performance gliders, thermal soaring gliders, like that people sit in and fly, real ones, full size. Why aren't they all flying wings? Well, flying wings just aren't as efficient. If you do everything right, then the conventional layout will still always be more efficient than the flying wing. Simple as that. Even though you lose the drag of that tail and you lose the weight of the tail, it's still not as efficient because we're losing Newtonian lift due to the reflex on the wing. So that's about that. But what we could do actually, if you want to reduce the effect a little bit, is, and most of the flying wings that I design, what have I done with my eraser? Oh, here it is. Use a piece of paper. What I've done with most of my flying wings is I do this. I use a symmetrical aerofoil like this. And why do I use a symmetrical airfoil? Well, one of the interesting things is that a symmetrical airfoil, or in fact, and I was saying before about flat plates, if we have a flat plate like so, it's just a sheet of foam board or something, they're actually quite stable. Because the centre of pressure moves much less on a symmetrical section and a flat plate than it does on a lifting section. If you change the angle of a symmetrical section, the centre of pressure doesn't actually move that much. And that means that you don't need nearly so much reflex on the back. So you don't lose as much Newtonian lift, but of course you don't get as much lift from the Bernoulli effect. So it's trade-off, balances, give and take. But I find symmetrical aerofoils make for far more stable flying wings. If you want something that's just going to groove. Now, it won't have possibly the same pitch stability, it won't be self-leveling because you don't have the same force from your elevons, but it will groove. You put it in a dive, it'll stay in a dive. You can make it neutrally stable, much easier with a symmetrical section, just like on a normal aircraft. Symmetrical sections are much more easy to produce a neutrally stable aircraft, perfect for aerobatics, than a lifting section. That's why all the best aerobatic aircraft have symmetrical sections, because it's just easier if you don't have to worry about the centre of pressure wandering all over the place, because the aerofoil is somewhat more stable in itself. There you go. So most of my wings, as I say, have symmetrical airfoils. But that's the lift side of things. That's why we have reflex. That's why reflex is important. That's why no flying wing will fly without reflex. It'll just lawn dart every time. Right, so what I'm going to talk about now is planforms, because that's important too. You know, the shape of a flying wing. We've got swept forward wings, we've got swept back wings, we've got planks. What difference do those factors make? Actually, I've just realised this video's gone on way too long already, so I'm going to stop it here. I'm going to do the planform issues in the next video, which will be coming up shortly, talking about those factors affecting when you look down on the wing, you look at the shape of the wing, what are the important factors there? And I'm also going to talk about things like yaw stability and why flying wings waggle a lot. You know, look at videos, FPV or high definition cameras on flying wings, they're often wobbling and pitching, and they just don't seem as stable, do they? And there's a reason for that, because they're not. And I'll explain why that is, why there's instability in pitch and yaw as well, even though we have this reflex and it should be giving us the stability we need, why it's never quite as good as on an aircraft with a conventional layout. Stay tuned for that. Now, if you've got questions, if I've glossed over stuff or if I've spoken too quickly, which I always do, then please put them in the comment section below and I'll do my best to address them. And if you want to see any other aspect of this explained, which I haven't already talked about, then I'll be doing that in the next video. If not, complain about it then. There you go. Fixed wing Friday, woohoo, who'd have thought? So I have a number of more flying wings which are being built, and so there'll be some practical stuff too. I might do a few little experiments just proving about the centre of pressure issue. I'll cut some foam board up and we'll make some wings in the next video so we can look back at this, and I'll also answer the questions. That's it, rambled on enough, goodness me, I don't know when to stop. Thanks for watching. Thank you to my Patreon supporters. Woohoo, you should have got a video today which only you have got. So in the meantime, time for me to clear the whiteboard, get back to the bench. Bye for now. G'day and welcome back to RC Model Reviews. Today, make a bit of room. God, what's going on here? It's terrible, no room. Here we go, got some room now. Right. G'day and welcome back to RC Model Reviews. Today I'm going to talk more about flying wings and the way various aspects of these wings affects their performance. And last time I looked at the longitudinal stability and how we used reflex in a wing to make it stable in pitch. And today I'm going to look at lateral or roll stability and yaw stability, right? Those are two other aspects that are quite important. I'm going to look also at something which is quite an interesting thing, the effect of a swept wing and why we have swept wings. Now, first of all, I want to talk a little bit first about levers. Levers, why am I talking about levers? Because they're crucial to today's discussion. And we all know what a lever is. You have a little fulcrum and you can have a bar or something. And the way levers work is when you push down on here, this end goes up. Now, if the fulcrum is in the middle, if the lever is an even length on either side, then there's no real gain. It just changes the direction of the force. But if you make a long lever, like that, then when you move this down here, the force here can be much greater. I think somebody said, give me a lever and I can, long enough lever and I'll move the earth. And that's true, because if this distance here was 10 times longer than that distance there, then for every unit of force you apply here, you'll get 10 units over here. So you magnify the force. It enables you to do a lot of work, apply a lot of force with a little bit of force. It's a force amplifier. And good examples of levers we use every day almost are things like spanners and ratchets, wrenches, because if you look at this, you get a nut. You can't undo it with your fingers. It's too tight, too tight. Put this on here, you've got a lever. All of a sudden, you've got a lever to turn that screw or that nut, and that gives you a lot more force. So levers are important. And the general rule of thumb is the longer the lever, the more force you can exert, right? Remember that. So let's go back to wings, because that's what we're talking about. But don't forget about levers. Whoops, oh no, what a mess. Anyway, okay, here's a wing. Looking down on it, we're looking at planforms, right? Today we're looking at planforms. What's a planform? Well, look, quick recap. That's a side elevation, right? See that side elevation? Front elevation, planform. Planform's when you look down on it, or conversely look up from the bottom, but it's the flat. It's when you're looking at it like that. So this is a conventional fixed chord straight wing. That's a wing, and we can make those fly. I've got, I use plank wings for my combat wings. They fly really well. But most commonly we're going to find in the hobby are swept wings like this. Excuse my crappy drawing, because I'm not very good at it. There's a swept wing, roughly, on Bruce CAD. Right, and you might say, well, why do we sweep wings instead of having them straight? Okay, they look faster, don't they? Swept wings always look faster. We're used to seeing swept wings on fast aircraft. Jet-powered aircraft often have swept wings. And one of the key reasons in full-size aviation for having a swept wing is because it reduces drag at supersonic or near supersonic speeds, transonic speeds. Because what happens is as you're going really quickly through the air piles up in front of your wing and you get a pressure wave that accumulates here, and eventually that becomes a shock wave when you reach the speed of sound. But as you get closer and closer, by having the wing swept back, you don't have that wave pushing on the entire wing surface at once. It only pushes on the front, and therefore you reduce your drag. So it's great. Airliners have swept wings because they can fly much closer to the speed of sound without encountering all the problems associated with being transonic. So that's a simple thing. But honestly, if you think you're going to get your bonsai anywhere near the speed of sound, you're dreaming. It's not going to happen. So that's not the reason we sweep our wings for models. There are a couple of other reasons. And it's all about levers. As I was saying, the most important reason for sweeping our wing is leverage. Because, as I mentioned before, we have a centre of gravity, right? Let's put the centre of gravity there. Typically that on a flying wing is 25% or so of the wing chord, because this is a constant chord wing. So what we actually mean is 25% or a quarter of the area of the wing is in front of the CG and 75% is behind it. Okay? So it's area. It's not actually it's on a fixed chord wing like this, a plank. It's easy to calculate because that line, it's, you know, the area, if it's 25% of the distance, it's also 25% of the area. Super, super simple. On a swept wing, not so easy, right? So on a swept wing, you have to calculate the areas. And you'll find on a swept wing, the CG will probably be, if we draw it like this, CG is probably about here, right? We've got 75% of the area behind the CG, 25 in front. Interesting thing happens here. Now, we need to get our CG forward. What can we use to position, what can we use to move the CG forward? Because you'd think, okay, normally a wing will balance it halfway, and this wing would balance probably, I don't know, we're way back here. So we need to get the CG forward using heavy items up the front. And on a plank, it becomes quite difficult because if we look at let's look at the bonsai. It's a little cutout here for the battery, right? That's quite a way up the front. So let's do this, draw the little cutout for the battery. And if we draw a line between there and the CG, you can see that is the distance. That's the distance of our lever. Back to levers. That's our leverage. Go onto the plank here, and if we put a battery in here on the leading edge, well, that leverage is a hell of a lot shorter because it's closer to the CG, closer to where we want the CG in the first place. So we have trouble getting the CG right with the plank because we can't get the battery far enough away to give enough leverage to move the CG forward. So what we have to do with the plank, generally speaking, is put a pod on it like this and put a battery up here. That restores this longer lever that we have with a swept wing. But swept wings are just a convenient way to get a CG in the right place without too much ballast or having to add pods and things. It's one of the key reasons. But there's another reason too, because again, we're talking leverage. And if we look at here's our elevons here, for example, right? Now, if we have elevons on this, like so, again, the distance here is pretty small. The distance here is massive. So here's a short lever, here's a long lever. So our elevons, and in fact the reflex on our wing is going to be far more effective because it's further from the centre of gravity. So it's going to be more leverage. This will be more stable in pitch because we've got our reflex further from the centre of gravity. That means this will be more stable, it'll be easy to balance. That's one of the two main reasons that we have swept wings. The other thing is we're going to have some fins on here, right? So if we put fins on here, let's put some fins on there. And then we put some fins on here. This is for our vertical stability, our directional stability, your stability. If we were to draw a line from the centre of the area of those fins, look at the lever we've got there. If we do the same here, well, that's a really short lever. So again, even our vertical stabilizer surfaces are going to be far more effective because they're a longer lever. It's almost like having a tail. We've almost built a tail into the wing by sweeping the tips back. We've got the benefits of a tail without the hassles and the weight and the drag and the extra complexity of having a tail. So swept wings improve stability, make it easy to get our model balanced in the right place. Wow, why aren't all wings swept? Most of them are, but I mean, what could possibly go wrong? What could be wrong? One of the problems we have though, swept wings are not perfect, and I'll tell you the downsides now. Okay, on the board I've drawn some arrows. Those arrows are the airflow. And here's our wing, ta-da! And let's say we're flying forward normally, then those arrows are sort of, the wind travels right over the wing, we get lift, all is good with the world, right? No problems at all. But what happens if our model yaws a bit? If we get a bit of a yaw on, a bit of turbulence kicks it around a bit, and it yaws? Well, some interesting stuff starts happening here with swept wings. First of all, most obvious thing to notice is that this half of the plane is now presented directly into the airflow. So it's going to have more drag because the air is hitting the front of this, and this is sort of trailing behind, so we get less drag from this wing that's trailing behind, which is actually a stabilizing effect, because if you imagine it, if we're pivoting around the center of gravity and there's more drag on this wing, it's going to pivot back. So it's going to be directionally stable. It'll be stable in the yaw plane. If it yaws off to the side, it'll naturally want to correct itself. And that's a good thing, right? Well, sometimes it is, sometimes it's not. But the other thing, which is actually not so good, is that if we're flying along like this and we yaw that way, then suddenly this wing's not only producing more drag, but more lift. Because this aerofoil is straight onto the airflow. This one is sort of trailing out sideways. There's less effective area. If you're looking along here, that's how much wing you see there. On this side, you only see that much wing. So this appears to be a shorter wing once it yaws, which means that it will actually try and roll. So if you are flying along and you yaw this way, you'll roll that way. So there is roll-yaw coupling. The yaw produces a rolling motion, and it also produces a corrective yaw motion. So you can see this, that you yaw, you roll, you yaw back, you yaw, you roll, you yaw back. And have we noticed on FPV videos that flying wings do this a lot? We do. This wobble, wobble, wobble thing is really common with swept flying wings flying FPV, because we have a situation here that's quite akin to mini quads or quadcopters, where you have a stabilization system. And if you don't get the gains right, you get oscillation. You know, you have too much P gain and your quad goes woo, 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 like this. You have too much I and it goes woo, like that. Same here. We've got a corrective force. We've got feedback which is trying to correct the situation with the yaw. And it's kind of like, I've got something I can demonstrate with. One moment, jump cut. That didn't take long. Okay, here we go. I have a plane, our model is flying straight into the wind. I'll put it in front of me so you can see. Flying straight into the wind, and it gets displaced. And it tries to go back to the original point, just like this spanner. But what does the spanner do? It doesn't go straight back. It's sort of woo, woo, woo. Eventually this oscillation will slow down and stop. But it actually has an oscillation. It goes one side, the other side, the other side. It's what we call a damped oscillation. And if the dynamics of your flying wing aren't dead right, then what you get is not a yaw and a correction, but a yaw, a roll, and then that gradually dies out like this. So yaw, roll, blah, blah, blah. And that's caused because of the roll-yaw coupling and the self-righting effect, or the self-correcting effect of the sweep on the wing. So it could be really good, but in most cases, because people don't know what they're doing when they design flying wings, you get this. And that's not what we want. But we see it so often with FPV videos of flying wings. They don't groove, they do the wibble wobble. And so let's talk about how maybe we can avoid that. Now, as I said, the reason we get the differential drag and lift is because the air over the wing is not traveling this way anymore, it's traveling that way. It's traveling there, and it's traveling this way. So the best way to try and avoid this wibbly wobbly effect, I don't know what that was. Oh, it says cable tie. Best way to avoid the wibble wobble effect is to try and keep the air always flowing as it should do over the wing. And it's been my experience. Now, other people may have different experiences, I don't know. But I have found, let me just erase this off the board and draw a new wing with my fantastic CAD skills. Here we go. Wait for it. Right, here is the wing. Actually, I'm really bad at this. I don't know why I even bother. I should, here we go. Here's our swept wing. And the air can come from either side. And it's worth noting at this stage, actually, just to make things, imagine the air's coming along here. If the model banks, and this is another effective sweep, if the model banks like this, then what it'll naturally tend to do is slip like that. You know, imagine if you put this on a perfectly smooth frictionless surface and you tilted the surface, it would slide down like that. And of course, the air is pretty much friction free. So if you get something kicks a wing up, then the wing will actually slide like this, which is the same as the air coming from a side angle, and that means these are self-righting. A swept wing tends to have dihedral effect. As it starts to side slip, the wing here gets the air flowing more straight on, and it creates a lift, so it will actually level it out. So in fact, on some large aircraft, you notice on some of the big, especially military aircraft, things like the Hawker Harrier jump jet, the Alpha jet, and even some of the big cargo jets with high wing mounting, they have anhedral, they have the wings droop down at the ends. That's to counter the dihedral effect of the sweep. So you end up with a nice negative or neutral stability. Otherwise, the dihedral effect of the sweep would make the thing really rock and roll. In fact, you get a lot of Dutch roll sometimes with swept wings. And that Dutch roll is this, woo, what we're talking about. It's Dutch roll. And it's a real problem, which is why a lot of aircraft have anhedral to cancel that out. And they also need big vertical stabilizers to also help there too as well. So anyway, back to what I was talking about. How are we going to stop the effect of this yaw roll coupling and this wibble wobble? Well, in my experience, and this is just my experience, the best and most effective way is to do this. What are that? That's wing fences. Wing fences, you've heard of those? They're simply a vertical surface that runs usually from the front of the wing to the back of the wing, front to the back. And what that's going to do, of course, if we look at it like before, let's say we are side slipping or we've yawed, the air that would normally go straight across here like this and create more lift on this wing is redirected by these wing fences so that it ends up coming off the back of the wing just as if there was no yaw. So you don't get the dihedral effect, you don't get the extra drag, and you don't get the extra lift on that wing, so you don't get the wibble wobbles. It helps direct it so the wing doesn't even know it's yawing, but it will, of course, it won't yaw any further. It has neutral yaw stability, which is kind of what you want, because then you don't get that oscillation going on, that backwards and forwards. It gives you a nice neutrally stable ship in terms of yaw, and also helps the roll as well, because you don't get the dihedral effect quite so much. Another factor is that even when you're flying forwards with a conventional swept wing, you get air coming in like this, and without the wing fences it tends to follow the sweep of the wing, so you get air flowing towards the tips because it's being directed that way by the wing. So you have this spanwise airflow. Spanwise airflow is really bad. It's not a good idea. You don't want that. It's not good at all. I'll show you why. Let me use my whiteboard eraser again. And this also explains why we often have tip fins on aircraft. Let's have a look. This is the front elevation of our wing, exaggerated of course. What normally happens is, let me get a pen, let me use a green one. In order to fly, we have this. This is a bubble of low pressure. That is to say, the pressure on the top of the wing is lower than the pressure on the bottom. Remember, we're looking from a front elevation here. So this is what we're looking at, that view there. And where we have nature abhors imbalance, right? I've told you that before. So we have lots of extra pressure on the bottom here, and we have low pressure on the top. So what tends to happen is that the high pressure tries to go in and equalize the low pressure. And that usually happens, air travels along the span, and it goes in here and tries to fill in the low pressure. The high pressure tries to creep around the edge of the wing and fill in the low pressure at the top. And if we look down on the wing, let's go here, draw another one. Now it'd be nice if I had some templates for these, wouldn't it? Here's our wing. Crap as usual, right? What generally happens is that the air from beneath comes up over here. Because the whole thing's moving forward, it doesn't just come straight up to the top, it actually gets blown back a bit, and you end up with what's called a tip vortex like this. So you get the spirally vortex off the tip as the high pressure on the bottom tries to get to the low pressure on the top. That vortex creates drag, it slows your plane down and makes it less efficient. So how can you avoid that? And of course the other problem is that this spanwise flow with a swept wing is reinforced by the fact that the air wants to travel along the wing instead of straight over it because of the sweep. So you're going to have even more spanwise flow, you're going to have even more tip vortex with a swept wing. So what do you do? How can you avoid that? Well, the answer is pretty damn simple. Put a damn wingtip up here and a wingtip up here. And then we find that the high pressure on the bottom can't reach the low pressure on the top. Right? So we don't have the huge vortex. We have a vortex, but it's nowhere near as big. And so, well, normally with this vortex, let me just draw this again so I can demonstrate if I can find the right pen. Here we go. Normally, without the wingtips, your actual top low pressure bubble doesn't make it to the wingtip because this bit's filled in by the vortex. Once you put the wingtip fins on, of course, then it can go all the way to the end. So it's like increasing the wingspan of your wing when you put these tip fins on. And that's why you'll see a lot of airliners have tip fins now. In fact, virtually all of the high performance airliners have winglets on the end to stop this vortex, which reduces drag and also effectively makes it look like it's got a longer wing because it's not losing that final bit to the vortex as such. Brilliant. Tip fins are a good idea. But this raises the whole question of, if I'm going to have fins, where do I put them? How big do I make them? What shape are they? And that really is another real Pandora's box of compromises and issues that I'm not going to go into here, because there'd be another whole video, so I'll cover that later on. But suffice to say, general rule of thumb, when it comes to fins and vertical stabilizers, is they want to be behind the CG. Whoops, that should be C and that should be G. You know what I mean? They should be behind the CG, because if they're not, they're actually contributing to negative stability. You know, it's like if you try and throw a dart backwards, you know, it'll flip around and go forwards because the center of pressure is in front of the CG. Well, it's the same with the wingtip. If we have our wing like so, let's have a look at our wing aerofoil. This is our flying wing with a bit of reflex. There we go. Here's the CG, like that. Now, if you have a fin that starts here and goes right up there, the bit, let's draw that. If we have a fin like this, well, actually this piece of the fin here is going to be working reverse. So you would lose an equal area in front here. So you'll have all the drag and everything of a big fin, but you won't get the effect of a big fin because two bits are cancelling out. So generally speaking, for fins, you want to design your fin so that all the area is in front, or sorry, is behind the CG. So design it like this, and then it's going to be far more effective. You don't want any in front of the CG. That's just working backwards. I've mentioned wing fences, and you notice that I said they could come to the front of the wing, and they should, to stop the span-wise flow. And that, you can do that with a swept wing, of course, because when you sweep a wing like this, your CG is probably about here, right? Maybe about there. So your wing fences, if you draw the line, even though they come to the front of the wing, they're still behind the CG. So then you can run them right up to the front. You can run them around the front if you wanted and run them underneath. That'd be the best way to do it, is have wing fences top and bottom of the wing. Stops all that span-wise flow, improves your efficiency, reduces your yaw coupling, stops the wibbly-wobbly. Well worth considering. So the other thing is, do you have, like if you're working with tip fins, if this is a tip fin, do you want any area under here? A lot of planes have area under there. The, what is it, the Tech 1 FPV 900 I'm putting together at the moment. It has tip fins that go above and below the centre line of the wing. Now, from a practical perspective, having tip area below the tip of the wing is just asking for it to get smashed off when you land. But from an aerodynamic perspective, there are certain benefits. It's going to add to the reduction in tip, or it's going to reduce the tip vortex even more. And so there are some real benefits to having some below the wing centerline, below the bottom of the aerofoil. So yeah, it's all compromises. And the best thing I can say is get yourself some foam board, cut it up, try out different things. Try planks, try swept wings. Someone's going to ask, what about swept forward wings? Well, that's a whole nother video. I'll cover it if you want me to. But suffice to say, I hope I've covered the basics here and I've explained why we get the wibbly-wobbly and one usually pretty simple solution with the wing fences. How high are the fences? Whatever. You have to practice. But, you know, just try stuff out. See what works. You can get some foam board, cut it to shape, a couple of dabs of hot glue, just enough to hold it, fly it, see if it improves it, increase the area, see if it gets worse or better. If it gets, and then you can trim it down to get the minimum size you need to make it work. That's the fun of this stuff. You can experiment. You're not like, McDonnell Douglas Skunk Works where every change costs millions. All it costs you is a little bit of hot glue and foam board. It's worth playing around with. And it's fun. It's something exciting. You learn something as you do it. So there you go. I hope I've covered some of the basics of wings, planform, roll stability, and yaw stability, and why swept wings are so, in some ways, good, and we're really forced to use them, and in some ways they're bad, and they make for really crappy handling planes if you do it wrong. That's it. Questions, comments in the usual place. And as I say, my usual disclaimer, I have simplified things for the purposes of making it easier to understand. I don't want to fill it all with calculus and algebra. I just want to get across the basic concepts using analogies and simple examples. So if someone wants to pipe up and say, that's not strictly true, yeah, you're probably right. But it's close enough that people can learn from this and apply what they've learned here to their own models, designing new ones or modifying the ones they've got. So give it a go. Let us know how you get on. In the meantime, thank you to all my Patreon supporters. Really appreciate it. Thanks to you, I'm still making these videos. Thanks for watching. Bye for now.